Hi everyone, my name is Zhao. I'm from University of Technology Sydney. Today, I will present our paper, Direct Bundle Adjustment for 3D Image Fusion with Application to Transesophageal Echocardiography. 3D image retracing and fusion is an important research topic that has attracted a lot of attention in the past decades, especially in the medical field, which involves various 3D imaging modalities like ultrasound imaging, computed tomography imaging, and magnetic resonance imaging. Registration and fusion are important for medical image analysis since they could combine valuable information conveyed by different images. Here are some examples of 3D image registration and fusion. Conventional methods separate image registration and fusion into two sequential steps. First, images which need to be fused are aligned in the same space. Secondly, these aligned images are fused together. Pairwise registration and fusion methods each time only estimate the transformation matrix between two images. Current 3D image registration and fusion methods for fusing more than two images are mostly derived from pairwise methods, which will incur accumulating errors inevitably. Compared with pairwise method, a better strategy is to optimize the poses of all local frames at the same time and distribute the errors evenly. Bundle adjustment is currently regarded as a golden standard for obtaining optimal frame poses of multiple 2D images in computer vision community. Most of BA algorithms are feature-based. However, there hasn't been a common method for 3D feature extraction. In addition, feature extraction is usually difficult in images with real distinct features, such as ultrasound images. Some published works use direct methods as a refinement step after feature-based optimization, so they cannot work independently. Importantly, all these works are still focusing on optimizing poses of the reconstructed 3D scene points instead of images. So, to our best knowledge, there is no BA method that can be used for multiple 3D image registration and fusion. In this paper, we proposed a novel direct bundle adjustment algorithm for registering and fusing a collection of 3D images simultaneously. The method can optimize both poses of 3D image frames and the intensities of the fused image. Compared to the conventional two-step process of registration and fusion, the proposed method completed the tasks in only one step. The figure on the left illustrates a scenario in which there are m frames of 3D images, and each image captures only a portion of the actual scene. Our objective is to obtain global poses of local frames and the fused image m. We parameterize the pose attached to each 3D image with 6 variable algebra, and denote the intensity of one voxel pj in the fused image m as the function of its coordinates, that is, mpj. Here, x is the overall state vector, where xk and xm are collections of all pose parameters and all intensities in the fused image m, respectively. The idea behind our proposed direct bundle adjustment is straightforward. We want to maximize the similarity between the fused image and the local images. In the figure on the left, the intensity mpj is fused from several corresponding voxels in different local images. In the rigid scenario, we can calculate coordinates of corresponding voxels pij by a Euclidean transformation matrix. Here, T xi maps the pose parameters xi to a rigid transformation matrix in Euclidean space. Then, we can calculate the intensity difference between voxel pj and its corresponding voxel pij in local frame ii, like this. Finally, we formulate the overall optimization problem as a least squares problem, like this. If we write the overall intensity differences as a concatenation vector ex, we can write the objective function like this one. In this paper, we use the Gauss-Newton method to solve the optimization problem. This is GA equation. We need to calculate the Jacobian of intensity difference vector to the state vector x. Here, Jij is one row of Jacobian matrix. Please note, Since intensity difference EIJ is only dependent on Xi and MPJ, only these two blocks are non-zero in Jij. Solving GN equation directly usually needs a lot of computation resources and time due to the large size of coefficient matrix. A 3D image usually contains millions of voxels in one single volume. Reconstructing a global image with several 3D images, the size of coefficient matrix of GN equation will be in the tens of millions multiplied tens of millions. As mentioned before, since every row of Jacobian matrix only have two non-zero blocks, this will result in a sparsity of the GN equation. If we write the step change of pose and intensity parameters separately, we can rewrite GN equation like this. Then, an intuitive illustration of the structure of coefficient matrix H is like this figure on the right. Here, HXC is block diagonal and HMM is diagonal. Such a sparse structure is similar to many other BA problems, and we can use short complement to calculate step change of pose and intensity parameters sequentially. In general, the size of HMM is much larger than HXC since the number of voxels in the first 3D image is much larger than the number of local images. But the inverse of HMM is easily computed by the inverse of each element on the diagonal. Solving the problem using short complement is much more efficient than solving original GN equation. The other strategy to speed up our implementation is to pre-compute gradient and intensity space. In the step of Jacobian computation, this term is the intensity gradient, which can be pre-computed in the local 3D images before GN iteration. In addition, when calculating corresponding coordinates Pij from Pj in first image, since the Pij are usually not integers, the intensities and the gradient values of voxels are interpolated to reduce the error of pose estimation, which are also processed before the iterations. The example here is a 3D transesophageal echocardiography image. 3D TE image is a type of ultrasound image which is widely used in clinical field. These are intensity space of the 3D TE image and its three corresponding gradient space. We use 3D transesophageal echocardiography image as an example and perform simulated and in vivo experiments to validate the proposed direct boundary adjustment algorithm. 3D TE images suffer from limited field of view. Registration and fusion methods are potential to overcome such a drawback by combining multi-view images. In both simulated and in vivo experiments, the proposed method is compared with commonly used sequential fusion method. As illustrated in the left figure, to generate simulated 3D TE images, we first crop a number of 3D images from a 3D CT Hz scan and then add white Gaussian noise on these cropped images. Our first experiment is to assess the accuracy of a proposed DBA method. We generate 5 sequences of 3D TE images with different poses, and then white Gaussian noise with a standard deviation of 8 is added to these images. There are 11 images in each sequence. We perform the experiments on these 5 sequences of image data by using the proposed DBA method and the sequential fusion method respectively. And the mean absolute errors of translation and the Euler angles are compared respectively in right top figure. The results show that the proposed method is much more accurate than the sequential fusion method for most of cases. In addition, we also calculate the mean absolute errors of intensities of the first global images with respect to the ground truth image, and the results are shown in Table 1. The smaller errors of the results from the DBA method indicates that the proposed method has better accuracy than the sequential method. Our second experiment is to assess the robustness of the proposed method to intensity noise. We generate one sequence of 3D TE images and 5 noise levels with the corresponding standard deviation of white Gaussian noise from 6 to 10 are added to the images respectively. The distribution of the mean absolute errors of translation and rotation calculated by the proposed DBA method and the sequential method is shown in the left figure. From the comparison of both errors, it is showing that the proposed DBA algorithm has much better robustness to the intensity noise than the sequential fusion method. The intensity mean absolute errors of the reconstructed global image using two methods are compared, and the results are shown in the table on the right. It is found that although the mean absolute errors of intensities obtained by the two methods increases with the increase of noise level, the results of the proposed DBA method is always better than that of the sequential fusion method. In vivo experiments, 3D TE images from 5 different patients are collected using a 2D array transducer with the assistance of the ECG gating technique to eliminate deformation in the collected images. The evaluation of the results are performed based on the quality of the global images and aligned images, since the ground truths of the in vivo datasets are usually not available in practice. This figure shows the fused images obtained from the proposed DBA method by comparing sharp boundaries in the single frame of images and fused images, such as left atrium walls, which are indicated by circles in the figure. It is found that the fused images obtained from the proposed DBA method have smooth transition and no misalignment or ghosting is found, which suggests good quality of the estimated global images. In addition, the field of view of the fused images are enlarged around 2 times as compared with the original single frame of TE images. To assess the accuracy of the pose estimation, images are aligned with the poses calculated by DBA method and the sequential method, respectively. 2 examples are shown in the top figure. From the comparison, we can see that the result of DBA has a smooth transition, while the result of sequential method has apparent misalignment. In addition, mean-squared errors between global images and the registered images is calculated for all 5 in vivo datasets. Smaller mean-squared errors of DBA method than sequential method suggest that the result of DBA method has better alignment than those of sequential method. Thus, all these results indicate that the proposed DBA method outperforms the sequential method in terms of pose accuracy. So in this paper, the proposed direct bound adjustment algorithm provides an elegant way to obtain the optimal global image and optimal local frame poses in one go without any information loss and information reuse. Simulated and in vivo experiments show that DBA method is robust to intensity noises and much more accurate than the conventional sequential fusion method. The current algorithm is still computationally expensive due to the large-scale optimization problem involved. In our next step, we will investigate strategies to reduce the computational cost. Thank you so much for your listening. If you have any questions, please feel free to discuss with us.